This is the video for our paper, Learning Part Motion of Articulated Objects Using Spatially Continuous Neural Implicit Representations. Articulated objects exist everywhere in our daily life. The space of 3D articulated objects is exceptionally rich in their huge semantic categories, diverse shape geometry, and complicated part functionality. Therefore, it is an important but challenging task for robots to perceive, model, and further interact with 3D articulated objects. For the modeling of articulated object, recent works need to train a separate model for each object category, or require articulation configuration annotations. Different from previous works, we propose a kind of novel articulated object representation that is generic to different kinds of objects and articulations. Specifically, we map the part motion to the movement transformation of points on the part, without requiring the part configurations like pose, movement direction, making it generic to different kinds of articulations and objects. Further, we build a spatially continuous neural implicit grid to smoothly model the point movement transformation. Given 2 point clouds of an object with different part poses, we aim to generate point clouds of the same object under query poses. Each point cloud is provided with the corresponding part pose label indicating the scale of its articulation. We propose a novel framework to tackle this problem. It is composed of 2 modules: spatial transformation grid generation and part motion generation. For spatial transformation grid generation, first, 2.NET++ with an attention layer encodes the 2 input point clouds into point-level features, with a 3D-UNet further encoding the features into a neural implicit grid with geometric information of the input point clouds. Then, we use MLP networks to encode the 2 part poses into 2 features, and concatenate them into the feature grid, making the neural implicit grid aware of part poses of the object. For part motion generation, we use MLP networks to encode the novel part pose into the feature, and concatenate the feature into the grid. We query each point in the input point cloud in the feature grid, and decode per point transformation to generate the object point cloud with the new part pose. For object generation with novel part poses in training categories, visualization demonstrates that our method reserves better object geometric details and smoothly generate parts than other methods. Besides, quantitative results also demonstrate our superiority over other methods. For object generation in novel categories, we first train the model on one category and fine-tune it on another category using 1/20 of the time used for training. The visualization results show that other methods fail to generate point clouds under correct poses, or cannot formulate parts in a proper way. We also implement interpolation and extrapolation to evaluate if the articulation part poses distribute continuously and densely in the representation. Given 2 shapes of the same object, we generate the object with novel articulation degrees in between or beyond. We denote the input parts with dark green and light green, and denote the generated part with medium green. We can observe that our method can reliably generate shapes under both inter and extrapolation settings, demonstrating that we have learned a continuous and dense feature for part motion. Besides, quantitative results also demonstrate our superiority over baselines in interpolation and extrapolation. We uniformly sample points in the space as queries to the transformation grid, and represent the transformation direction by arrows. The visualization shows that our proposed neural implicit grid smoothly models the point motions on the part. Thank you for watching.